So welcome to the first fall picture language seminar. We're very happy to resume this fall. We tried to resume in a dual mode in the lecture room, but this week it didn't work. Perhaps it will next week. It's really wonderful to have as our first talk Cynthia Dwork. Cynthia is an expert on privacy, and we'll talk today about differential privacy, the mathematical bulwark against re-identification and reconstruction. Cynthia.
Hi. Good morning, and thank you for inviting me to join you today. Let me share my screen. There we go. And I assume you can all see my slides?
Looks beautiful.
Great. So I won't be watching you. So if you need to get my attention, someone has to say something. And I certainly won't be looking at the chat. So I'm happy to take questions. All right. So yes, so I'm going to talk to you today about differential privacy, which is it's a term that now refers to a collection of algorithmic and complexity and lower bound techniques around for statistical analysis of large data sets. And you'll understand why I chose the particular subtitle, the Reidentification and Reconstruction, later on. Okay. So this talk in a nutshell, there are two kinds of analyses that come up when one considers privacy preserving data analysis. So one of them is like statistical understanding of the population as a whole, for example, as we do with census data, or analyzing loan data for evidence of systematic discrimination, or even in machine learning, as we train a classifier to distinguish images of healthy brain cells from cancerous ones. The other kind of privacy in data analysis that one might hope for is sort of the dream in the Total Information Awareness Program, which was aimed at finding terrorists, where somehow you want to find a needle in a haystack while at the same time protecting the privacy of all of the non-needles, all of the, the pieces of straw. Now, differential privacy is for the first kind of privacy preserving data analysis. I don't even know how to define, let alone achieve, privacy for the second kind of analysis. If the second kind is what you have in mind, this is the wrong talk and these are the wrong techniques. They're not appropriate. Okay, so let's think about statistics. A statistic is a quantity that's computed from a sample. And we like statistics because we can look at them and we think that they will tell us something about the population as a whole, if we've used good sampling procedures. And in fact, two data sets that are collected independently from the same population and with the correct methodology, we expect are very likely to tell us essentially the same things about our population. And there's a sense of privacy that's derived from this fact. In other words, people might think, well, these are just, it's an aggregation. Nobody knows that I'm in the sample. I could claim that I opted out. In some way, people feel that it's not about me, my data in a sample. Okay. And this is sort of on the right track, but it needs some help, as we'll see. And differential privacy provides this help. In fact, differential privacy will preserve this I could have opted out sense of privacy for every computation, including total population counts. So it extends this, I might not have been in the sample or I could have opted out. It extends those semantics to quantities computed on the population as a whole. So how do we abstract the problem? Well, we imagine that there is a database that has sensitive information. There is a data analyst who is adversarial and who is trying potentially to compromise privacy. The data analyst could do it by accident, but might be intending to do it. And the analyst makes queries to a data set and receives responses or answers. And as these responses come back, she formulates adaptively her next queries based on all of the transcripts so far, and so on and so forth. A query now is any computation on the data. And so that really broad abstraction captures, first of all, the actions here of multiple data analysts who are acting either in a coordinated way or not. The formulation of studies or queries as studies based on past studies, and even the generation of synthetic data that looks like real data and that mirrors their statistical properties, but which somehow or other are created in a privacy-preserving fashion. So privacy-preserving data analysis dates back at least to Warner's 1965 paper on randomized response. And in this work, which was begun in 2002 with my then intern, Adam Smith, census for us was the driving scenario, the analysis of the people's data for the benefit of the people, to apportion the people's resources, and with a legal mandate for privacy. Uses of census data include apportionment of representatives to the US House of Representatives, the allocation of hundreds of billions of dollars, billions with the B dollars in federal money, redistricting, and enforcing voting rights. Okay. So let's use flossing as an example. So whether you floss regularly or not is a sensitive attribute in this talk. Let's go back to the just statistics intuition. And let's ask, how many members of the House of Representatives floss regularly? So your sense is probably that if you get the answer to this question, you really haven't compromised anybody's privacy. You know, some number of them, some fraction of them will floss regularly, some of them don't, and doesn't seem to be disclosive in any way. But suppose you got the exact answer to this question and you got the exact answer to this one. How many members, other than the speaker, floss regularly? So if you know the answers of both of them, you can take the difference and you can determine whether Nancy Pelosi flosses regularly or not. So even though each of these queries is a query over a large number of people and aggregates the answers from a large number of people, their difference is disclosive.
Just a small question. So I'm assuming that there's like a restricted subset of queries you can make on this database that forced you to ask these two specific questions rather than just, let's choose this member, does this member floss, correct?
No. You can certainly ask, does this member floss? And obviously, if you get the right answer to that, it would be disclosive, right? But many people feel that if something is a statistic taken from a large set, then there's privacy. And so the point of this example is to show, while that might be true once, sort of, it's definitely not true in combination with other such questions.
I see.
Okay.
Thank you.
Yeah. So no, I'm not forcing you to ask over large sets. I'm just pointing out that asking over large sets is not in and of itself completely protective. Thank you for the questions. Good. Okay. So the differencing attack is actually just one example of how seemingly innocent queries over large sets can be combined to compromise privacy. And in fact, the so-called fundamental law of information recovery or reconstruction states that overly accurate estimates of too many statistics completely destroys privacy. Okay. And the definition of overly accurate here is tied to the definition of too many. If you want to have just a couple of statistics, then in order to thwart this attack, you can add not very much noise. But if you want to handle many statistics, then you must really start adding lots and lots of noise. So this actually says a lot of things that we only realize after some years of thought, which is that it applies equally to interactive as to non-interactive systems. So any kind of blob, any kind of blob that you could publish that would allow people to then obtain relatively accurate answers to the questions of their choice will turn into providing overly accurate estimates of too many statistics. Okay, so you can't publish a blob that makes it possible to answer all queries pretty accurately, or even, as it turns out, more than a 1 minus 0.29 fraction of them. And the fundamental law is kind of what we're up against. This has absolutely nothing to do with differential privacy. This is just a law of math. And in fact, this work by Dinur and Nissim that formulated what are called reconstruction attacks and analyzed them predated the definition and the construction of differential privacy. Okay, great. So let me get now to the definition of differential privacy. First, I'm going to motivate the definition and then discuss its meaning, and then we'll get to the formal definition. So here's our database. And in the database are the data of Cecilia Helena Payne-Gaposchkin, who was among the first women to obtain a PhD in astronomy and the first person to obtain one at Harvard. And she ascertained the temperatures of the different classes of stars and estimated the great abundance of hydrogen in them, much more than there is on Earth, while doing the research for her dissertation. So her research contradicted the belief at the time that the sun and the Earth had similar composition. So definitions are essential, and without them, we literally do not know what we're talking about. So what do we mean by privacy preserving data analysis, and what kind of protection should we want to offer Cecilia Payne? So a natural candidate, and certainly the one that I first tried, was articulated by Tordellinius in 1977. And what it says is that the data analyst can't learn anything new about Payne by interacting with the database. So Payne could be an extrovert, and she might have published all sorts of things about herself, and in modern times, maybe on the web, and that's fine. And we don't want to publish the statistical database for revealing things that are already known in public. But what we want is that interacting with the database shouldn't allow the data analyst to learn anything new about Payne. So the problem with this is that, in this case, what's the point of the database? So suppose I'm from Mars and I believe that all people have 2 left feet. And in particular, I believe that Payne has 2 left feet. And I interact with the data set and I learn that the vast majority of humans have 1 left foot and 1 right foot. And so what I conclude is that it's much more likely that Payne has 1 left foot and 1 right foot. I've learned something about her. Now the question is, have I compromised her privacy? And this may be a matter of opinion. Ideally, I would learn the same things about Payne, though, even if she's replaced by some other random member of the population. In this case, Henrietta Swan Leavitt, who was the first to note a relation between certain variable stars' peak brightness and the period over which their brightness varied, which proved a valuable means for measuring distances across space. So if I've learned the same thing about pain, even if I take her out of the database, or we take her out of the database and replace her with Swan Levitt, has her privacy been compromised? And we decided no. We decided that if I learn the same things, even if I make small perturbations to the database and I remove the person or replace this person with one or two others and so on, then this is not a compromise of pain. So that gives us the English language definition of differential privacy. It says that an outcome of any analysis is essentially equally likely, independent of whether any individual joins or refrains from joining the data set. So before we turn this into math, are there questions? No? Okay. So in fact, we're even going to guarantee that if an analyst knows both the data set that includes pain and the data set without pain, so these are two data sets that are almost identical, only the one above the line has one more person in it, and that's pain. And even if the analyst knows all of her data and all of the data of everybody else, we're going to actually ensure that the analyst can't tell which is the real database that's being used to answer the queries. And if the analyst can't even tell, even when the analyst knows these things, then clearly nothing is being leaked when the analyst doesn't know these things about pain. Okay. So an adversary knowing both data sets in their entirety will never be able to distinguish. Now, when we say that the outcome of the analysis is essentially equally likely, we have to say, what is the source of uncertainty in the word likely? And the answer is that the algorithm is going to flip coins. So we're never going to rely on sort of luck in creating the database. Our definition is going to be worst case over all databases. And uncertainty is going to be intentionally introduced by the algorithm. This is good because the algorithm is written by us. We're the good guys and it flips coins the way it's supposed to. So the right kind of uncertainty will be released. Now, this is going to be a really, really strong definition of privacy. And you might wonder, why is it possible at all to do any kind of useful data analysis? There's like this proverbial sense of conflict between utility and privacy. And just a glimpse of why it works is that this idea of having like the same distribution or similar distribution on outputs when databases are very close, this is a stability notion. And stability is known to yield generalizability, that if you have algorithms that are stable to small perturbations in the data set, when you run machine learning algorithms that are stable in this sense are able to generalize for instances that are not in the database. And in fact, stability is now known to be essential, to be required for generalizability. So we see a sense in which privacy, our kind of privacy, and generalizability are now completely hand in hand and not in conflict with one another. And in fact, differential privacy protects against overfitting and p-hacking that you get in exploratory data analysis, but that's beyond the scope of the talk. Okay, so privacy and generalization are aligned. Good, so here's the definition. Now I need to explain a few terms before we can understand the definition. First of all, sometimes PowerPoint advances on its own, okay. Our algorithms are called mechanisms and they're denoted by the letter M. So M is just an algorithm that operates on a data set. And my data sets in this equation are going to be called X and Y. Now, differential privacy is not binary. It's not that something sort of is or isn't, but differential privacy has a parameter, which is almost always called epsilon, which in some sense governs the total amount of privacy loss. So it will give us a measure of privacy loss. So epsilon is something greater than or equal to 0. And we need the concept of an adjacent data set. So adjacent data sets, X and Y, are data sets that are identical, except that one of them is larger than the other and contains the data of just one more person. So you saw a pair of adjacent data sets on an earlier slide, the data set with pain and the same data set, but with pain's data removed. Okay, so those are adjacent data sets. So an algorithm is said to give us epsilon differential privacy if for every pair of adjacent data sets, X and Y, and every possible output event, S, the probability that we observe S when the algorithm is operating on X is at most e to the epsilon times the probability that we observe S when we're operating on adjacent data set Y. Remember that when epsilon is small, e to the epsilon is about 1 plus epsilon. So this says that these probabilities are pretty close. Moreover, there is the definition is symmetric in X and Y. So we also get the reverse inequality with the roles of X and Y swapped. Okay. Epsilon is called a bound on our privacy loss, and we'll see more about that. And the probabilities on the left and right are over the coins that are flipped by the algorithm. So the things that are under the control of the good guys. So this is a statement about the behavior of the mechanism, right? And this is a statement that the mechanism can ensure independent of what the observer actually knows. It doesn't care who knows what. It doesn't care what the analyst knows, what other things the analyst may know about pain by looking at pain's website and Twitter feed and all these sorts of things. And differential privacy is future-proof. From all external sources of information, there is nothing that the adversary can find out that will allow her ex post facto to determine whether the algorithm was operating on X or on Y. So you can learn things about pain under differential privacy, but you can only learn things that you could have learned without pain. Okay. In other words, you only get to learn things about the population as a whole. And rearranging the definition, just rearranging the terms a little bit, we see that this ratio is bounded by e to the epsilon, and sometimes that's called a bounded ratio condition. All right.
Sorry, just one question.
Yeah.
What if the data sets are really tiny? Then this definition doesn't apply, correct?
Wrong.
Oh.
Wonderful question. What will happen is you'll get a lot of noise, but you won't get a signal, but you'll definitely get privacy. And that's kind of the point. If the data set is very small, then kind of anything you learn about the data set really is learning about the data of each individual, just on an intuitive sense. So we're going to have to add enough noise that's going to swamp the presence or absence of one person. If the data set is really tiny, that's going to be a lot of noise, but relative to the size of the database. But we were thinking in terms of internet scale data sets, and this was just not an issue. And in fact, that brings up kind of an anecdote, which is Kobi Nissim came to visit me when I was at Microsoft, and he was telling me about his work with Reidentification and the Reconstruction attacks. And they viewed this as like the end of the world for privacy. And because there were polynomial, you only needed for one of their attacks, you only needed to add like ask a quasi-linear number of queries, of counting queries, in order to compromise privacy. Quasi-linear in the size of the database. And I was thinking about the Hotmail user database. And so I was thinking about hundreds of millions of users, and that was not an issue. Nobody was going to get to ask that many queries without being caught. So great. So this is why I said earlier that it's a collection of techniques for the statistical analysis of large data sets. Yeah, but privacy will always be maintained. Okay, great. Good. So as I was saying, this is sometimes called the bounded ratio condition. I may refer to that later. All right. So getting back to the haystack, the needle in the haystack, here's why differential privacy is just the wrong technique. Imagine that one data set is the haystack without the needle, and the other data set is the haystack with the needle. So what differential privacy says is you'll never be able to determine which of these is the case. So you can't use it to find the needle. And as I said at the beginning, differential privacy is just the wrong technique for this kind of problem. And I don't know actually any technique that solves it, but that's another story. Okay. Good. So what are the key properties of differential privacy? First of all, as I noted earlier, it's future-proof. So it's resilient to present and future information that comes from sources other than the database itself. It composes gracefully and automatically. So we have developed tools to understand the cumulative privacy loss over multiple computations. At worst, the losses add up. So if you have a database and you run an epsilon 1 differentially private query over it, and then you run an epsilon 2 differentially private query over it, the cumulative loss over the two executions is at most epsilon 1 plus epsilon 2. But you can do better than that, and we'll see something about that later. The consequence of composition is really important. It says that differential privacy is programmable. So think about regular programming. In regular programming, you could solve every problem completely from scratch, but the way you really do things is you create various primitives and subroutines and building blocks, and you attach them together in intelligent and creative ways to do things efficiently. So in the same way, we can create differentially private building blocks for various kinds of computational tasks, and we can combine them in creative ways so as to control the cumulative privacy loss in the best way possible for the thing we are trying, the analysis that we're trying to carry out. And so just as in ordinary programming, you might try to minimize the total amount of computation time and total amount of space. In differentially private programming, you also want to minimize the privacy loss, the cumulative privacy loss. And that, of course, is where all of the power of this technique comes in, of these techniques, this approach comes in. So let me tell you one technique for differential privacy. This is not the only technique that's really important, but it will give you some intuition, some sense of what goes on. So the Laplace mechanism, I'll explain this in a minute and why it's called Laplace, but I need a notion of sensitivity. So the sensitivity of the function is, it's a property of the function, not a property of the database. The sensitivity of a function is the worst case over all pairs of adjacent data sets. Remember that adjacent data sets are identical, except one of them has the data of just one more person in it. So it's the maximum of the absolute value of the difference between f of x and f of y on adjacent databases X and Y. In other words, it tells you in some sense how big a gap your noise is going to have to cover in order to obscure the fact that it is one database rather than an adjacent database. So this is a picture taken from Wikipedia of various copies of the Laplace distribution for various parameters. So we're going to be looking at Laplace, adding Laplace noise that from a Laplace distribution that has mean 0 and parameter B. And so here's these pictures. So what does the function say? It says, let F be any real valued function that maps data sets of some number n of elements to R. And I really should have had, instead of an n, I should have had a star. It just takes databases and maps them to reals. Then if we add noise that is drawn from Laplace distribution with parameter the sensitivity of F, which again is only about F, it's not about the actual database, divided by epsilon, we will get epsilon differential privacy. So let's just look at this for a minute. When the function is very sensitive, delta will be large and we'll be adding a lot of noise. And that makes sense because we have to do a lot of work to hide the presence or absence of somebody because F is changing a lot as we add or delete that person. When we want really good privacy, epsilon is small, and there's epsilon in the denominator. So again, the parameter is going to be large when epsilon is small. So the right things are happening. So things have the right shape. Now, before we see the proof of this, let's just say what it means for the most common kind of query that we talk about, which are counting queries. Counting queries are queries of the form, how many people in the database satisfy property P? How many people in the database like to play the violin? How many people in the database floss regularly? We also do fractional versions of that. What fraction of the people in the database do these things? Okay. So the sensitivity for a counting query is 1. Delta is 1. And so what this says is that we're adding noise that's sort of scaled to 1 over epsilon to get epsilon differential privacy. We tend to think of epsilon as a constant, like 0.01 or something like that. So on a large data set, this means that we're adding noise that's scaled to approximately 100 for a counting query. On a large data set, that's a vanishing amount of noise, proportional to the counts. It's a lot of, it's a very, very little bit of noise. Okay, so the proof for the Laplace mechanism is very simple, and it relies on the fact that the probability density function P of t will drop off exponentially in the magnitude of t divided by the parameter b. There's also a normalizing 1 over 2b term, but that's going to divide out. So for any t output that could be produced, the ratio of the probability densities of the output t on adjacent databases x and y is given by e to the f of x minus t over b if the database is x, divided by e to the f of y minus t over b when the database is y. So by the triangle inequality, that's bounded by e to the f of x minus f of y over b. And that's always less than the sensitivity of the function in the numerator. And so, and b is chosen down here as the sensitivity divided by epsilon. So the deltas cancel out and we get e to the epsilon. And that's the proof. It's a one-line proof. Now, it extends nicely to queries that instead of being real valued are RK valued. So K tuples. And that could be that you're asking K distinct counting queries, or it could be something else in high dimensional space. And the theorem now with the same proof says that if we add in now we have to change the definition of sensitivity to be the L1 norm of f of x minus f of y, which when k is equal to 1 is just the absolute value. And what the algorithm now is, draw independent noise scaled to the new definition of sensitivity over epsilon for each of the k coefficients independently, and add that to the outcome. Okay, great. K counting queries in this case would correspond to having to add noise that's scaled to now k over epsilon, or k when epsilon is a constant. But let's look at the histogram query. So in the histogram, we take the space and we arbitrarily carve it into a collection of cells. And we're asking for each of these cells, we're taking the space of data points, and we're asking for each of these cells how many people live in this cell. So for example, the cells might be income brackets, and we're asking how many people in the database have incomes between 10,000 and 20,000, between 20,000 and 30,000, 30,000 and 40,000, and so on. Those would each be different cells. But you can carve your population up in lots of different disjoint ways. And so the histogram query is saying, for this way that you have carved up the population, what are the counts in each of the cells? And histograms are, of course, the workhorse of official statistics. Well, what is the sensitivity of the histogram query? Even if it has a huge number of cells, the sensitivity of the query is just 1, because adding or removing one person from the database will change the count of only one cell, and it'll change that count by only 1. So the sensitivity for the whole query is just 1. And so the theorem says it's enough to add noise that's scaled to 1 over epsilon to each of these cells rather than k over epsilon. So that's a huge win. Okay. Now, a lot of times people look at relaxations of differential privacy, and the first relaxation is often known as approximate differential privacy or epsilon delta differential privacy. And the reason for the name epsilon delta is that the definition is modified to add this small delta term. So in other words, things can go wrong in a sort of delta fashion, a delta amount. And we tend to think about delta as very, very small. Like what we had in mind when we suggested this was what we call cryptographically small deltas that are smaller than 1 over any polynomial in the database size. But yes, why? Why should we relax? Well, one reason for relaxing is it lets us use Gaussian noise. And the nice thing about and it's not clear to you yet why you can't use Gaussian noise, but trust me, there's a little bit of a problem, which we'll talk about in a moment. The nice thing about using Gaussian noise is that when we define sensitivity, it's enough to look at what's the L2 sensitivity rather than the L1 sensitivity, which, say, for the case of k counting queries, could improve things by a factor of about square root of k. The relaxations will let us, so it turns out that when you're actually running a differentially private algorithm, privacy loss is actually a random variable, and we will define privacy loss formally, so you'll see what I'm talking about. And when you decide to engage with that fact, you can exploit the fact that privacy loss is a random variable. And this will lead us to something called the advanced composition theorem and other relaxations, such as, in particular, concentrated differential privacy. And we will get to that. But also the delta is a general escape hatch. So you can use cryptography to simulate a trusted center. And as long as the crypto system isn't broken, you can now run differentially private algorithms in various sorts of distributed fashion, relying on cryptography to help you carry out the computations of the trusted database holder in a really secret fashion. So there's some small chance that somebody will crack the crypto system. That's the delta. But other than if that doesn't happen, then everything is fine. You can use it to make some nice connections to robust statistics. So robust statistics have a similar flavor, and they are literally robust to small changes in the data set. However, they are not, robust statistical guarantees are not worst case guarantees. They are high probability guarantees over the choice of the data set. It says when you're choosing your data set, if you're choosing it, if nothing really weird happens in the choice of data set, then things will behave nicely. Differential privacy says no matter how bad it is, how weird and fluky your data set is, we're going to still guarantee privacy. So what we get to do using epsilon delta differential privacy is use a differentially private test to see whether the data set looks normal or not. And if it looks weird, then we'll quit. And if it doesn't look weird, we can proceed and use the nice robust estimator. And there's a small chance that we will think that it's fine when it isn't, and that's captured by delta. Then also we can use, say, approximate differential privacy to get rid of the dependence on the number of cells if we look at the worst case error for histograms. So there are lots of nice things you can do. So now let's talk about the privacy loss of random variable. So when we argue about differential privacy, we look at pairs of adjacent data sets and we look at the ratio of probabilities of various events under one data set and under the other. So let's fix a pair of adjacent data sets, X and Y. And now our real database, the one we're operating on, is X. And we're going to run our algorithm M on database X and we'll get an outcome. And we look at we define the privacy loss of that outcome as the log of the ratio, and I'm abusing notation here, probability density of M of X. So we're looking at the ratio of the sort of the probability, so to speak, of observing C when the database is X divided by the probability of getting it when the database is Y. And when it's continuous, these are densities, okay? So just to see what I'm talking about, let's say the real database is X. M is giving me some noisy version of some function f of X. And so the curve on the right is the distribution, the probability distribution on outcomes. Outcomes are given by this axis here, the x-axis, sorry, it's called the x-axis, this axis. The curve on the right is showing the distribution on outcomes when the database is X. The curve on the left is the distribution on outcomes when the database is Y. And you can see, of course, that every outcome could be obtained with whether the database is X or Y, but just with different probabilities. So this privacy loss is the log of the ratio of these heights, okay? Now, when we're using an epsilon differentially private algorithm, the magnitude is always bounded by epsilon. Notice that sometimes the privacy loss can be negative. This is a log of two probabilities. When the guy in the numerator, when the numerator is larger, this is going to be positive. When the numerator is smaller than the denominator, the privacy loss will be negative. So in this picture, the privacy loss is negative for every outcome that's, under the red arrow. Once we get to this point, if the database is X, the probability for seeing these points is all smaller when the database is X than when it's Y. Those are the cases that we get negative privacy loss. And that brings us to the Gaussian mechanism. So for Gaussian, we draw some Z according to a normal distribution with mean 0 and variance sigma squared. And we add this noise to the outcome of the function, to the value of the function. And we have to say what delta F, what the sensitivity, what sigma squared should be. But just sort of notice that the privacy loss is going to be less than or equal to epsilon when the log of the probabilities of observing an outcome that is Z away from F of X, when the ratio of the probabilities is e to the minus Z squared over 2 sigma squared in the numerator. And well, this shifted amount is shifted by the sensitivity when we have the database Y. So, so when this log is less than or equal to epsilon, the privacy loss will be bounded by epsilon. So we suppose that we take sigma to be delta F over epsilon itself. And this delta F is the L2 sensitivity. When the draw from the normal distribution is bounded by sigma times 1 minus epsilon over 2, we're going to get a privacy loss less than or equal to epsilon. That's this. We may have other cases where it's less than epsilon, but it will be less than epsilon at least this often. So the animation on this slide didn't work. Ignore the blue text for a moment. What happens when we get too much noise? When we get too much noise. So first of all, this is why the Gaussian mechanism doesn't give pure differential privacy. Some weird things happen in the tails. Okay. On the other hand, if we fail to get a small z, we're still pretty likely to get a pretty small z. So when we fail to be in this range, we don't have death and destruction. We don't have a total loss of privacy. Most likely the privacy loss will be at most 2 epsilon. And in fact, in general, the probability that the privacy loss would be larger than t times epsilon is just the probability that the draw is larger than sigma times t minus this term. And that's falling off exponentially in t squared. So with by going through these analyses, we know how we have to set the variance in order to ensure epsilon delta differential privacy. We end up with this term log 1 over delta hanging out, or 2 times log 1 over delta hanging out there. And that's a little annoying, but it can still be good when the sensitivities, when we're looking, say, at large numbers of counting queries. Now, but what I want you to really take away from this is this statement, the purple statement. When we're using Gaussian noise, the probability that we are T epsilon privacy loss is dropping off as exponential in T minus T squared. So now let's look at composition. First of all, we need to define what we want in composition. And because I want to have time for other things, I'm going to actually elide this slide, and we're only going to talk about multiple queries on one database. But in general, we wanted to consider what happens in a world in which the adversary got to choose collections of adjacent databases that could be overlapping. And these could be the database at Facebook, God forbid, or the database at the hospital and lots of other places. And one person's data would be in many, many different data sets. But I'm going to skip this for now. So just think about applying many computations to the same data set. The techniques extend. Basically, recall that privacy loss is sometimes negative. So that means that when we do multiple computations, we can get cancellation. Sometimes it'll be positive, sometimes it'll be negative. It's a little more likely to be positive, but sometimes there's negative, so we get cancellation. And the flavor of the result that we get is that for every epsilon and for every delta simultaneously, the composition of k different epsilon differentially private algorithms is satisfies k times epsilon squared plus this square root of k, this term, times epsilon comma delta differential privacy. So the key point is that instead of being k times epsilon, which is what we were getting before, we're getting something that looks more like square root of k times epsilon. And that's a really, really big advantage when you want to answer many queries. And the proof, which we won't go through, basically has two steps. For each of the epsilon differentially private mechanisms, we argue that for any epsilon differentially private mechanism, the expected loss is bounded by epsilon squared. Actually, the original bound we had was 2 epsilon squared that was improved by, I'm sorry. Yeah, Kairouz, O, and Vishwanath. Okay. So the expected loss at each step is at most epsilon squared, and the magnitude of loss at every step is bounded by epsilon because it's differentially private. And so the privacy loss random variable is actually a martingale, and we can apply the Azuma-Höfting bounds. And what we're getting here is that, so the expected loss over k iterations by linearity of expectation is bounded by k epsilon squared. And then this comes from Azuma-Höfting. And so what we're getting is that for every t, the probability that we get t standard deviations beyond expectation is falling off exponentially in t squared. And we saw that before, right? That's exactly what we were getting with the Gaussian. So these are two things that existed in sort of independently, and now we're going to see a strong connection that we get to use. By the way, this result also applies to composing epsilon delta prime differentially private algorithms, and then you get this k delta prime term here.
So there's a question in the chat about why you use Gaussians. I think you've answered it though.
Yeah, because it lets us scale to the L2 sensitivity instead of the L1 sensitivity, and that can be a big improvement. Thanks. Okay. Last technical point I want to make is that this is the starting point for something called concentrated differential privacy. Concentrated differential privacy, I'm only going to say something about it from a very intuitive level. To apply the composition theorem and have a cumulative loss of epsilon, we have to force each of the things that we are applying it to be something like epsilon over root k, differentially private with high probability. Then when we multiply by square root of k, we end up with an epsilon. So to apply it directly, we have to force each of the individual things to be high probability, very small. But when we're looking at high degrees of composition, we don't need everything to be so well behaved. We only need that over time things behave well. And this lets us be a little less conservative in each computation. We don't have any death and destruction if we miss some of the bounds by a little bit. We don't need this high probability guarantee for each of the steps. We can relax that. What is a place that we've relaxed it? Yes, in the Gaussian. where we showed that, oh, well, we might fail to be epsilon differentially private, but then we're really likely to be 2 epsilon differentially private, and the possibility of having a privacy loss that looks like T epsilon is exponentially small in minus T squared, and so on. So the bottom line is that with this approach, you can get rid of the square root log of 1 over delta factor in the standard deviation for the Gaussian mechanism when we're doing it in the context of lots of composition. So the cumulative loss is the same, but our accuracy got a lot better. Why am I jumping up and down about this? Because this is the version of differential privacy that the Census Bureau used. And so now we're going to get to the Census Bureau. Oh, I should just mention, there is a really, really rich algorithmic literature that deals with lots of different kinds of differentially private algorithms for lots and lots of different kinds of problems. A lot of work right now is on deep learning and various sorts of gradient descent. Also new models. You can ask me about that in the question section. And there are lots of applications beyond privacy, but I want to talk about the census. So skip this. Oh, and it's widely used in practice, lots of places. Great. So let's get to the census. So this year, for the first time, the Census Bureau will use differential privacy as its primary means of disclosure avoidance for the decennial census. And census was actually the original motivation for our work when Adam and I started doing this in 2002, as I mentioned earlier. And like voting, the census is located at the heart of representational democracy, and it affects long-term outcomes and the distribution of benefits. And the potential harms of privacy loss are severe. So for example, the discovery of the violation of conditions of Section 8 subsidized rental, housing assistance for which a family might have waited for years, can result in eviction and homelessness. So people say, oh, I don't have anything to hide. Well, actually, a lot of people do have things to hide. And this is an example that not many of us tend to think about. So this is John Abel, the chief scientist and associate director of research and methodology at the Census Bureau. And what he said was that the techniques that were used for disclosure avoidance in 2010 census don't suffice. And what he's referring to here is the Reconstruction theorem, the fundamental law, allowing people to reconstruct data from tables that were previously assumed to be privacy preserving. And he gives this wonderful talk that you can find on the web, Staring Down the Database Reconstruction Theorem. And he talks about an attack, like the reconstruction that the Bureau did. So they reconstructed putative individuals from released summaries and tables in the 2010 census. They linked putative people without names to names by using commercially available databases to acquire personally identifiable information. And they compared the ground truth to the confidential data. They compared the ground truth of the confidential data to their reconstructions and reidentifications. And they found that they were correct on 17% or 52 million individuals. And for those individuals, they were able to exactly reconstruct the race and ethnicity. So they identified people and reconstructed their race and ethnicity. All right. Now, there's been a lot of debate over the significance of this attack. Objections include that the reconstruction has errors and the attacker can't have confidence in the conclusions drawn, that you can guess race and ethnicity with, say, probability 2/3 by guessing the majority value for the census block. I'll call that guess construction. Now, because the Census Bureau did not release a paper on its findings, we don't actually know whose data were correctly reconstructed. Was it the data of the outliers or the data of typical people? We don't know. They didn't tell. Was it children? Children are not in commercial databases. Was it children? Did this happen in small census blocks where guest construction doesn't work well, or only in large census blocks? We don't know. Now, this was an unsophisticated attack. They used an unsophisticated attack, and they only used a small subset of the billions of released statistics when they did their reconstruction. And in fact, operationally, the research team was, when they got what they got, when they had gotten that distance, they were told to stop expending resources on reconstruction and start building the tools that were needed to protect against reconstruction. So they only went a certain distance and then they were told stop. Now, when the privacy community heard about the reconstruction, they said, well, yeah, of course, we know that with these kinds of numbers of statistics, we're going to have reconstruction. And so from the perspective of the privacy and cryptography community, this was just the canary dying in the coal mine. More statistics, more sophisticated techniques will naturally lead to better reconstruction. And I worry about the weaponization of census statistics by hate groups and by child predators, by people who want to create and market lists of children of specific ethnicity in a given age range, or people who want to create and distribute lists of gay couples. This is not a question of my neighbors already know I'm gay. This is bringing me to the attention of strangers who live in neighborhoods where I don't feel comfortable living, where I choose not to be. And now there's considerable effort being directed at developing a theory of attacks, including how to measure their efficacy and also the practice. And I think it's realistic to expect some strong results in the next couple of months. And in the best case, these efforts will be hand in hand with algorithms for generating synthetic data from statistics. Differentially private statistics in the sort of good algorithmic case, and when there's no differential privacy or the privacy loss budget is set too large in the attack case. And some recent work by Idor, Brown, Kearns, Kentapati, Mellis, Roth, and Siva along these lines seems heuristically to also give a method of ensuring high confidence on reconstructed records. So I should probably stop now. This is what the Bureau says. And I think that the Bureau deserves enormous credit for modernizing the privacy protections. But the Data Stewardship Executive Committee chose privacy parameters that take us outside where the theoretical guarantees are meaningful. And that brings up challenges along the lines of, there are a lot of people asking for super accurate statistics, and there's nobody advocating for privacy. So all of the pressure on the Data Stewardship Committee is toward reducing the privacy guarantees. Challenges moving forward in terms of research and also use. Data consumers, demographers, gerrymanderers, and voting rights advocates alike, urban planners, social scientists, nobody's trained to interact with data in a differentially private way. Basic tools of statistical inference in the presence of noisy statistics still need to be developed. And there's work going on in this direction. There's a workshop that's being planned, but this is inescapable. The use of differential privacy has brought to the attention of a much, much wider community the fact that the data released by the Census Bureau are not exact. The numbers are not exact. It has, at the very, very, very best, it would capture reality on April 1st of each decade. But there's all sorts of undercounting and differential undercounting and lots of ways in which people decline to answer certain kinds of questions and so on and so forth. There are many, many sources of uncertainty. And I hope that dealing with differential privacy, where we understand exactly how the noise is being introduced, will be just a first step in learning how to deal with uncertainty in statistical inference more generally. So thank you, and I'm sorry for running a little late.
Thank you very much, Cynthia, for a beautiful introduction to this subject, which is extremely interesting and important. So I'd like to open the floor to questions. Please turn on your video when you ask a question.
I'm going to stop sharing so we can see everybody.
Well, let me start by asking, you mentioned L1, L2, L infinity norms. Are there any more sophisticated types of analysis that come into this?
There's a lot of sophisticated analysis that comes into it. There are techniques used from geometry for dealing, for example, with something called the projection mechanism. There are the concentrated differential privacy and related work involves it involves oh gosh, I'm sorry, I'm blanking on a term. So yeah, it involves various kinds of divergences, lots of different kinds of divergences. So we use KL divergence already in the finding the expected privacy loss, but the privacy loss random variable in concentrated differential privacy is sub-Gaussian, and that's often best viewed in terms of statements about higher kinds of divergences. Those are examples. A lot of, yeah. Okay. What else?
Are there any other questions? Looks like, Arthur, you were about to say something.
Well, I didn't want to ask, this may be a technical question, but it's something that I missed in the theorem you had mentioned earlier. Like you started out with a collection of databases and a function on them that was like what the information you were given, and then you concluded something. Somehow an epsilon came into the picture, and I don't know exactly where it came from, if you had defined it from that input, like this function and your database set. And it was like, right.
How about if I, so you said there was a theorem?
Yeah, you had this theorem that said, let F be this function from databases you define delta 1.
Great.
And then, yeah.
Here?
Yeah, exactly. I guess I just wasn't sure
Good.
what the input information was into this theorem and what the output was. Like, did you get a probability distribution as an output? And then, sorry, yeah.
Okay, great. So suppose, okay, great. So suppose F is just any real valued function that you might run on a database. Think counting query because it's so intuitive. Suppose I want to release an estimate of f of x for a database X, and I want that I will do this in a differentially private way. Then the following technique works. First, I compute f of x. Then I draw I take a random draw from the Laplace distribution with parameter the sensitivity of f divided by epsilon. So I need this epsilon here because I want to give an epsilon differentially private release. So I have chosen epsilon. Epsilon is public for everybody to know. The function is public for everybody to know. The database is secret. And my draw from this distribution, my actual draw from the distribution is secret. So I add my draw from the distribution to f of x, and I release that sum. That process is an epsilon differentially private algorithm for releasing f of x.
So that is now the M for
Yes.
okay,
Yes.
okay, great.
Yes.
Thank you. Thank you.
Right, good. Okay, and then for the Gaussian mechanism, instead of drawing from the Laplace, we're drawing from a Gaussian with some appropriate variance. Yeah. Okay.
So maybe now a less technical question. So I don't know, I just heard about this now, but like you said that these are now applied in the 2020 Census Bureau. What was maybe like your first moment where you had applied it in like a larger scale situation?
Oh, that's a good story. So there is a product, a Census Bureau product mentioned in the slides, which is a tool for allowing people to understand where people work and where workers live. And it's called On the Map. And in, I don't know, 2009 or 2010, I was giving a talk about differential privacy, and somebody in the audience said, "You guys, you invented that in 2006. When is it ever going to be built anyway?" And yeah, I'm a theoretician. I don't build things, right? Anyway, I said, I don't know. I try to get the product guys at Microsoft to do it, but they say that people aren't demanding privacy. That is changing, by the way, but in any case, so I couldn't get them interested in it. Anyway, and somebody in the audience said, it's built, it's running at the Census Bureau. And I said, well, really, how do you know? And he said, I built it. And that was Ashwin Makanavajala. And so that was that product. So that was the first time that I knew it was actually being used. And their paper was 2009, so it was around then.
So Christian has a question.
Hi, thanks for the great talk. I had a question about you mentioning the connection with robust statistics, but saying that in robust statistics, often you actually care about guarantees only with high probability. But in your introduction of this epsilon delta, approximate differential privacy, is there something similar going on? Do you only want, like with probability 1 minus delta, to be close? Is there more direct?
Great question. So there's two different things. There's high probability over choice of the database, which we can't control at all. And there's high probability over the run of the algorithm, which we can control because we are flipping the coins. So in robust statistics, it's high probability over choice of database. In differential privacy, it's high probability over the coin flips of the algorithm.
I see. Oh, I see how they're very different.
So ours remains a worst case guarantee over choice of databases, X and Y.
Thanks.
Yeah, right. So recently there have been some very, very nice developments in high dimensional robust statistics. I was looking at robust statistics in about 2009, but things have really changed dramatically in the last couple of years. And now we're starting to see some differentially private versions of these high dimensional median, for example. It is really nice.
So if there are no further questions, I'd like to thank you again, Cynthia, for an absolutely wonderful introduction. Very beautiful talk. And
thank you. Nice to meet you all. Bye-bye.
Yes. See you again next week. Bye-bye. Bye-bye.